Alright, now in this lecture video we're going to look at a few more examples of the Kruskal-Wallace test. So in this example, this is example 3.5, we're going to compare the lifetimes of 4 brands of automobile tires. So a consumer reporting organization conducted an experiment to compare the lifetimes of 4 brands of automobile tires in order to make recommendations. 24 automobiles were available for the study. To each of the 4 tire brands, 6 automobiles were randomly assigned to use that brand. The cars were then driven until the tires were deemed to be in need of replacement using an objective wear and safety. The lifetimes of the tires are found on the following slide. Alright, so here's the data. You can see here that we've got 6 observations for each brand, the lifetime of the tires on each of the 6 cars that use that particular brand. So the lifetimes of the tires for the 4 brands are given in the table below. The question of interest is whether there is sufficient evidence at the 0.05 level of significance to conclude that differences exist among the 4 brands of tires. Alright, so the hypotheses are that the lifetimes of the 4 tire brands are the same against the alternative that differences exist in the lifetimes of the 4 tire brands. Alright, so let's remember the procedure. We rank all the observations in one combined sample. So in this case we've got 4 samples, each of size 6. So we're going to put all those observations into a single sample, a single data set that's got 24 observations. We rank the observations with respect to the outcome measure, in this case the lifetime. We're going to sort those in increasing order, creating an ascending data array, and then we assign the ranks as we usually do. Once we have that, we're going to separate the samples back out so that we have 4 samples of ranks, and then we're going to compute the various summary measures for those samples of ranks, in particular calculating the rank sums for the samples. And so doing that, here is a data set that contains, instead of actual lifetimes, contains the ranks of the data. Now, to the data set of ranks, I've appended or augmented a few extra columns. I've got a column here for the rank sum for each of the tire brands, and these will be used in the analysis. I also had the average rank for the ranks within each of the 4 tire brands, and we can actually use the average rank looking at this by eye and get an idea of whether we think there are differences, and if there are differences ultimately when we perform the test, it'll begin to give us an idea of where the differences are. And so in looking at this, just nothing formal, but it looks to me like the lifetimes of tire brands A and B are about the same, and that they may be different than the lifetimes of tire brands C and D, and C and D may actually be different from each other as well. Alright, so there are ties in the data. Going back here, we see that there must have been ties because we see some 0.5s. Although that's not always the thing to look for. If you'll notice that we also had more than 1 7 in here. So we see that there were 3 observations, it looks like, that were tied. So it must have been ranks 6, 7, and 8 that were tied, and therefore each got the rank 7. Okay, so since there are ties, this is the formula we're going to use. We use this in the other examples as well because those examples had ties. So we've seen this formula before. The reference distribution is the chi-square distribution. The degrees of freedom associated with the test is going to be equal to k minus 1, where k is the number of groups. There are 4 groups, 4 tire brands in this case, so this is a 3 degree of freedom test, and we're performing the test at the 0.05 level of significance. So the critical point is going to be the upper 5th percentage point of the reference distribution, the chi-square distribution with 3 degrees of freedom, and that value is 7.815. So the rejection criterion is to reject the null hypothesis if our test statistic H is greater than 7.815. And so now we have to calculate the value of the test statistic. I'm going to use a spreadsheet again. I've got this spreadsheet template that I created that I've shown you in the other 2 examples that we've done. And I just expanded it a bit to account for 4 groups instead of 3, which we had in one of the other examples. And so you can see here that I've entered, I should have changed that from method to brand. I thought I did that. And then I should have changed this titling here from score to mileage. But anyway, I've got the data entered here, and then I sorted it based on the mileage, and then computed the ranks. And here is an expanded view of that spreadsheet. So you see here that I've got columns for my R sub ij's for my 4 groups. So these are the ranks of the observations within the 4 groups. So we sort the data increasing on mileage, compute the ranks associated with those values, and then we separate out this column of ranks or this data set of ranks into the 4 samples. And then I need to square those, and so I've got 4 columns out here for the squared ranks. Then I've got these calculations which are using these values to calculate the value of the test statistic. Alright, so here is a composite slide showing all the 2 slides I've already shown you, the snippets or the screenshots of the spreadsheet, but I also have down here the actual value of the test statistic H. The test statistic H is 8.4682. Alright, and so the conclusion at the 0.05 level of significance, since the test statistic 8.4682 is greater than the critical point, 7.815, the rejection criterion has been met, and so therefore we reject the null hypothesis and conclude that the alternative hypothesis is true. Putting this back into the language of the problem, we can say that there is sufficient evidence at the 0.05 level of significance to conclude that differences do exist in the lifetimes of the 4 brands of tires. Now obviously we wouldn't stop here, we'd want to drill down and try to find out where the differences are. You know that in an ANOVA setting we might look at all pairwise differences to see where the differences were. Alright, so I also want to point out that what would be the conclusion at the 0.025 level of significance? So how significant is the value of the test statistic 8.4682? At the 0.025 level of significance, the critical point is 9.348. Again, obtaining that from the chi-square table. And since the test statistic 8.4682 is not greater than 9.348, we would fail to reject the null hypothesis at the 0.025 level of significance. Now, since we would reject the null hypothesis at the 0.05 level of significance, but not at the 0.025 level of significance, it must be the case that the p-value is strictly greater than 0.025 and less than or equal to 0.05. So we do have bounds on the p-value, so this constitutes an interval approximation of the actual p-value. So that is the end of this example. In the next example, example 3.6, we're going to investigate the relationship between the Kruskal-Wallace test and the Mann-Whitney test. What exactly do we mean by that? If you remember, when we first started talking about the Kruskal-Wallace test, I characterized it as a generalization of the Mann-Whitney test to more than 2 populations. So the Mann-Whitney test is used when we want to compare 2 populations with respect to location using independent samples. And I said that if we want to generalize that, we want to go beyond just 2 populations. And so we're looking at comparing more than 2 populations, again using independent samples. And I said that the Kruskal-Wallace test was a generalization of the Mann-Whitney test. Another way to say that is that the Mann-Whitney test is a special case of the Kruskal-Wallace test when you are comparing 2 populations. And so that is the way in which we're thinking about this comparison. So what we're going to do is go back to a previous example where we use the Mann-Whitney test. We're going to apply the Kruskal-Wallace test to that same situation because we can do that, right? The Kruskal-Wallace test is applicable for comparing the locations of 2 or more populations, and so we can certainly use it to compare the locations of 2 populations. And so that's what we're going to do, and then we're going to compare those results to what we got when we used, in this case, the approximate Mann-Whitney test. So the data in the table on this slide are from example 3.1, in which the Mann-Whitney test was used to determine whether or not cables made from 2 alloys differ in strength. And I see that, boy, I'm getting really beat up here by this autocorrect. All right, so at some point I'm going to fix that, but I'm not going to take the time to do it now. So in this example, we're going to reanalyze the data using the Kruskal-Wallace test. Here we have the original data from example 3.1, and these are the measured strengths that were given to us. The hypotheses to be tested. The 2 alloys are the same in terms of the strength of cables, against the alternative that the 2 alloys differ in terms of strength. All right, now in that example we found the ranks of the observations, and so I've reproduced those ranks in this data set. And I've also appended at the bottom here some summary statistics for the ranked data. What we're essentially doing here is replacing the actual value with the ranked data. And so for alloy A, the rank sum is 106. The average of the ranks for alloy A was 13.3. And then the rank sum for alloy B is 65, and the average of the ranks for alloy B is 6.5. Now, in calculating the ranks, we sorted the data in ascending order. We created that ascending data array. Larger or greater strengths correspond to higher valued ranks. So the stronger the cables are, the higher their ranks are, and so the higher their average ranks within the sample. And so it looks like, based on this, alloy A has a higher average rank than alloy B, and so we might expect, just based on this alone, without having done any analyses beforehand, that alloy A appears to be producing cables of higher strength. But again, the question is, even though there's a difference, how do we know it's significant? And what that means is the difference that we observe here, the difference in these average ranks, 13.3 versus 6.5, is that a big enough difference to lead us to conclude that in general, at the population level, alloy A produces stronger cables? So that's the question that we are trying to answer. And I think that by including these summary statistics along with the ranks, we're able to see what's going on and get some useful information here. Now, in this case, there are no ties. In fact, let me go back to that previous slide. You'd have to kind of look carefully through here, but there are no ties. So according to the notes, we're going to use this formula here. It's a little bit simplified. So we don't have to calculate that quantity S squared, which was then in the denominator for this test statistic. Now, I'll do this in the context of the spreadsheet and show you the value in a second. All right, but first let's look up the rejection criteria. So we are performing this test at the 0.05 level of significance. We've got two types of cables, A and B, and so the number of degrees of freedom associated with this Kruskal-Wallace test is K-1. So 2-1, or 1 degree of freedom, and you can see that right there. And so the critical point is the upper fifth percentage point of the chi-square distribution with 1 degree of freedom. All right, and that value, looking it up in the chi-square table, is 3.841. Okay, so now we're going to calculate the value of the test statistic. And so here we have the spreadsheet showing the alloys and the scores. Now, okay, so and again, what I'm doing here, I'm using this spreadsheet that I've created, the spreadsheet template that I've created to implement the Kruskal-Wallace test. And so you can see here I did remember to change the column headers there. Okay, so what I've done here is I entered the data. I initially had the observation numbers running from 1 through 18. And then I sorted the data on the strength. Well, actually, so I said I changed the headers. I forgot to change that one. So I changed the alloy, but forgot to change that to strength. All right. But anyway, so then I assigned the ranks. And so that's what I've done there. And then zooming out, this is the whole spreadsheet. I've only got two groups, so I only need these two columns and then these two columns. So I've simplified the spreadsheet. And then here is the composite slide showing those two slides. And then showing the information down here at the bottom. Now, in the previous examples, we had ties, and so we had to use the bottom formula on that one slide, the one that has 1 over S squared in it. And I've labeled that one H1 here. And that formula gives me a value of 7.1053. Now, because there are no ties in this data set, then we use that more simple formula, and that's what I'm calling H2. So I'm using both formulas to calculate a test statistic here. Because there are no ties, this is what the note calls for, but this is what we used before, and you can see that we get exactly the same thing. Now, the reason I wanted to show you this is just to show you that that simplified formula, this is just a special case of the formula we've previously used when there are no ties. So what that means is, for example, if you build a spreadsheet like I have, and you've got the formula built in that has 1 over S squared in it, you can still use that formula without having to change it because you are going to get the same value. All right? Now, let me tell you what you cannot do. Don't use this formula if there are ties. Use the other formula. Okay, so the value of the test statistic is 7.1053. And so since 7.1053 is greater than 3.841, the rejection criterion has been met, and so we're going to reject the null hypothesis and conclude that the alternative hypothesis is true. All right? And let's see here, so what cut and paste error, hold on. So fix that. So there is sufficient evidence at the 0.05 level of significance to conclude that the two alloys differ in terms of strength. We know that we reject at the 0.05 level. What about at the 0.01 level? Well, note that the critical point for the 0.01 level test is 6.635, and since our test statistic 7.1053 does exceed 6.635, we see that we would reject the null hypothesis at the 0.01 level as well. Now, what about at the 0.005 level? Well, the critical point for a 0.005 level test is 7.879, and our test statistic 7.1053 does not exceed that. So we would fail to reject the null hypothesis at the 0.005 level of significance. So since we would reject the null hypothesis at the 0.01 level of significance, but not at the 0.005 level, what we can conclude based on that is that the p-value of the test, while we don't know it exactly, we do know for a fact that the p-value for this test is greater than 0.005 and less than or equal to 0.01. All right, so that's useful to know. Okay, now we're going to investigate the relationship between the Kruskal-Wallace test and the approximate Mann-Whitney test. Okay, so what I want us to do is let's think back to when we did the large sample approximation to the Mann-Whitney test back in that section. I have brought those slides forward here just to refresh our memories. And so this is back in the continuation of example 3.1. We were doing this large sample approximation, and we had these statistics that were required for the analysis. So we've got the two sample sizes, and 1 is equal to 8, and 2 is equal to 10. And then the test statistic. Remember, for this large sample approximation, the test statistic t is always t1, and that was equal to 106. Okay, then we had to calculate the mean and the standard deviation of the sampling distribution of the test statistic. All right, and so we had those there. The mean is 76, the standard deviation is 11.2546. And then we specify the rejection criteria. And remember, again, that the reference distribution for this approximate test is the standard normal distribution. And so I'm getting these critical points from the standard normal table. And then we calculated the value of the test statistic, which for this approximate test is equal to t, which we found to be 106, minus the mean of the sampling distribution of t, all right, so minus 76, and then we divide that difference by the standard error of t, which was 11.2546. And so, rounded to 2 decimal places, we found that the test statistic is equal to 2.67. And then from that, we also calculated the p-value of the test, 0.00758. And then we concluded, because 2.67 was greater than 1.96, or equivalently, since the p-value, 0.00758, is less than or equal to 0.05, then the rejection criteria have been met, and so therefore we reject the null hypothesis. Okay, so we're reaching the same qualitative conclusion here using the approximate Mann-Whitney test as we did with the Kruskal-Wallace. So now we're going to look at the relationship between the test statistics for the Kruskal-Wallace test and the approximate Mann-Whitney test. So the test statistic for the approximate Mann-Whitney test, we rounded it to 2 decimal places, 2.67. I'm going to show more precision here to demonstrate what I'm talking about. So to 5 decimal places, that test statistic is 2.66558. We found the test statistic for the Kruskal-Wallace test was equal to 7.1053. Now, if you square this value, if you square 2.66558, you're going to get 7.1053. All right, and so for this example, the Kruskal-Wallace test statistic H is equal to the square of zcalc. It's equal to the square of the test statistic for the approximate Mann-Whitney test. The other thing is this. Even though I haven't included this on the slide, let's go back here. The critical point for this approximate Mann-Whitney test is 1.96. Now I want you to get out your calculator and I want you to square 1.96. I want you to square 1.96. What do you get? Well, you get 3.8416. Well, that was the value of the critical point for the Kruskal-Wallace test in this situation. So the Kruskal-Wallace test statistic is the square of the approximate Mann-Whitney test statistic, and the Kruskal-Wallace critical point is the square of the approximate Mann-Whitney critical point. And so what this is demonstrating, it's certainly not a proof, but it's demonstrating a general result. The result being this, that the approximate Mann-Whitney test and the Kruskal-Wallace test are equivalent when comparing two populations. Another way to say this is that the approximate Mann-Whitney test is a special case of the Kruskal-Wallace test when you apply the Kruskal-Wallace test to comparing two populations. And finally, one other way to say that is that the Kruskal-Wallace test is a generalization of the approximate Mann-Whitney test to more than two populations. Okay, so that's an interesting relationship that you need to understand. You need to know that and understand that. When you're comparing the locations of two populations, the Kruskal-Wallace test and the approximate Mann-Whitney test are exactly the same test. They're equivalent tests, just done in slightly different ways. In the case of the Kruskal-Wallace, the quantities that we're calculating are essentially the square of the quantities that we're calculating in the approximate Mann-Whitney test. Okay, so that's the end of this lecture video. So at this point we've seen 4 examples now of the Kruskal-Wallace test, and I hope that you're getting a pretty good feel for how to do it. It's actually, if you think about the various tests that we've looked at, the various nonparametric tests, the Kruskal-Wallace is actually, I think, perhaps the easiest to do by hand. So that's the end of this video, and we'll meet up again in the next video.